This video concisely discusses circuit applications of junction field effect transistors. It contains biasing methods, equivalent circuits or models, and junction FET amplifier circuits. In case of bipolar junction transistor circuits, these topics had been taken up separately in separate videos. Since the methods and procedures have been quite similar to that of BJT, they have been accommodated in one video here. Note that BJTs are preferred devices for most linear applications, while junction FET is preferred for switching applications. Now we'll start about the basics. Like pinch off voltage in junction FET separates ohmic and active region of drain curves. Another important factor is the transconductance curve is unaffected by the circuit configurations. While biasing junction FET's gate to source voltage is always reverse biased. Voltage divided bias is the most common bias type, as in the case of BJT. Small signal models for low frequency and high frequencies are different only by additional capacitances added to each pair of terminals in high frequency model. Note that the current gain in a junction FET amplifiers is undefined, so that there are only three amplifier parameters like voltage gain, input resistance, and the output resistance. A table gives various parameters for common source, common drain, and common gate configurations. Typical parameter values are compared for FETs and BJTs. BJT common emitter and common base circuits are found to give much higher voltage gain, while junction FET, common source, and common drain circuits have much higher input resistance. Other functions are similar. Now we start with the junction FET biasing model and amplifier circuits. First we'll give a little introduction. Field effect transistor is a three-terminal unipolar device. It has extremely high resistance, it's less noisy, and it has a better thermal stability. It's well known. But the only disadvantage is that it suffers from small gain bandwidth product. BJT is a preferred device for most linear applications, and FET finds applications for switching. We'll see some of the basics about the FETs. FETs are easier to fabricate, and they take less space on the chip, so they are less costly. FET is a normally on device, and its maximum ID is for gate to source voltage of 0. Pinch off voltage is one of the very important parameter for this. FET is a value of VDS where ID levels off with the VGS is equal to 0 value. And VGS off is the value of VGS that pinches off the channel, that is ID is 0. These have been some of the basics for these FETs. Now we'll give the symbols and corresponding drain characteristics for the FET. If you look into the symbols, this is a symbol for N-channel junction FET. This is the gate, drain, and the source. We find here this gate is arrow is pointing towards the channel. This is in the case of N-channel, and this N-channel symbol where gate is offset, it's not in the center, is also a symbol for the N-channel MOSFET. For P-channel MOSFET, the arrow is in different direction. Now this indicates the drain curves here. This is the junction FET. VDD is drain supply and VGG is the gate supply. And this is the point here. Here VGS is taken as 0. This circuit, this was 0 gate bias. And you can observe here this is the characteristic between ID and VDS, drain to source voltage. So if we observe this characteristic, we note here the initial region here, from here to here up to VP, this region is said to be the ohmic region, and from VP to this flat region is said to be the active region of the junction FET. So what we observe here is the VP is the voltage that separates the two regions, the ohmic region and the active region. So VP separates ohmic region and the active region. We observe here one of the very important characteristics of the FET is the Transconductance Cap Gm Curve. This is a curve between ID versus VGS. This VGS on the left hand side is the negative value of VGS, and so this curve ID versus VGS, the transconductance curve, the equation for this is ID is equal to the IDSS 1 minus VGS over VGS off whole squared, where IDSS is the drain current when gate to source voltage is 0. And this basically is a square law device, as is obvious from its characteristics. This curve is unaffected by the circuit configuration. Something very important is that this curve is not affected by the circuit configurations. And the unit for this is mhos or the Siemens. That is the unit for the transconductance. Now we'll observe here some of the important FET relations. We'll see here. The first is the ohmic resistance that we have seen. So at the pinch off point, the RDS is given by VP over IDSS. This is the ohmic resistance at the pinch off point. Now if you work near the origin, then it's defined as RDS. This is VDS over ID. Now second parameter is gate to source cutoff voltage, VGS off. This is minus VP, or more precisely we call it VP, the pinch off voltage, and VGS off. These voltages just magnitude is same, but one is negative while the other is positive. Now the drain current ID is IDSS 1 minus VGS over VGS off whole squared. It's a very well known relation. Now transconductance GM is assume delta ID over delta VGS for VDS is equal to constant. This could be written as GM taking from the above relation. You can find the GM is GM0 into 1 minus VGS over VP, where GM0 is defined by minus twice IDSS over VP. This GM could also be written here 2 over VP in terms of drain current and IDSS value at the 0 value of the VGS. Now drain resistance another parameter is defined as delta VDS over delta IDS. This is for VGS equals constant, and there is an amplification factor like it used to happen with the tube. Mu is the amplification factor, that is delta VDS over delta VDS over delta VGS. This is delta VGS. This is for ID constant. This is delta here. This is for ID constant. And the last relation here is mu is equal to GM RD. It used to be in the case of vacuum tubes, mu is equal to GM RP. It's a similar relation here in the vacuum tubes. Now we'll see the biasing part for the field effect transistors. We observe here that Q point for this is selected in the active region when we want to operate it in the amplifier mode. Okay, and the important point is gate to source junction is always reverse biased, and cell bias and the voltage divided bias, which is quite similar to BJT bias circuits, are the most commonly used bias circuits here, and these two have been considered here. What we observe here is this is a circuit for the cell where RG is this cell bias resistor being connected here, and this ID minus VGS. We observe here that VS, this is the resistance at the source terminal, that is IDRS. ID would be same here as well as here, so IDRS, and we can write VGS equals to VG minus VS. We want to write VGS, that would be VG minus VS, and here we know VG is 0 since this is a very high value of resistance, so this will be 0. So this VGS turns out to be minus IDRS. So we get Q2 and Q1. There are two operating points here, Q1 and Q2. These are because of the large variation of the FET parameters. Since two FETs have very different parameters, so such variation takes place. Now this is a voltage divider bias. As usual, R1, R2 are the potential divider. Resistors RD and RS are the resistances here. So this value of VG is R2 over R1 plus R2 VDD. As usual, ID is VS over RS, VG minus VGS over RS. Approximately you can write here VG over RS, since VGS could be taken approximately 0. So this turns out to be VDS equal VD minus VS. So the advantage here is the large VG here, because this value is large as compared to VGS, so it sums out the variations from one FET to other FET, because there are changes in FET parameters, and because of that it takes care of those variations. Bias approximations for these circuits are about 10%. That means these values are correct to the value of 10%, and most common bias arrangement is the voltage divider bias, as in the case of BJTs. Now small signal models here. If we see these models, what we have different models for low and high frequency. This is here a low frequency model. So here the gate to source junction is replaced by a very high resistance RGS, and why the output has been replaced by a voltage controlled source, that is voltage controlled current source, that is GM-VGS, and RD is the resistance, drain resistance. So this is the equivalent circuit model for the FET. If you want to replace it by voltage controlled voltage source, this could be drawn in this fashion. This RGS is the resistance and this is mu VGS RD, and where mu is GMRD is obvious. High frequency model, here high frequency model, you can see the values here for the high frequency model are the same here, except these capacitance have been added here to each junction here. This is gate to drain, there is CGD, then the value is CGS, and then CDS. All these capacitance have been added here. If you observe, these capacitance values are typically given here, CGS and CGD, they are about the same, about between 1 puff to 10 puff, while CDS, drain to source capacitance, is a smaller value, that is 0.1 picofarads to 10 picofarads. Now we see about the junction FET amplifiers. Junction FET amplifiers, here what we observed here is current gain of the junction FET amplifier is an undefined quantity. Why it is undefined? Because the input current is very small, that's nearly 0 microamperes. If the current is so small, you cannot define the current gain. So input signal should never, and the other point is input signal should never forward bias gate source junction. This restriction that should not be done. Now this is a common source amplifier, and governing equations for the common source amplifier circuit are given here. If you observe here, this is VG. VG is the value of the voltage at this point, that R1 over R2 or R1 plus R2 into VDD, and ID is VS over RS, and VD is VDD minus IDRD, and RD is the AC resistance at the output, that is RD in parallel with RL. So this is, and the gain is given by AV gain, voltage gain is given by GMRD, and here this phase shift is 180 degrees, so gain you could write as AV is minus GMRD for this particular case. Now if you consider common drain amplifier, you can see here the drain is common drain amplifier. Here the output is taken from the source terminal. Here again VG is taken R1 over R1 plus R2 into VDD, and VS is nearly equals to VG. VGS has taken 0. ID is VS over RS, and VDS is VDD minus VS. And the gain relation AV is GMRS over 1 plus GMRS. Here phase shift is 0. And the AC load resistance at the output is RS in parallel with RL value. Now this table here compares the performance of common source, common drain, and common gate FET amplifiers. For the common source amplifier, what we observed is the gain is, voltage gain is given minus GM into RD in parallel with RL. Input resistance is R1 in parallel with R2. These are the biasing resistors. Now R0 is given by RD in parallel with RL. This is for common source. And common drain, this is AV is GMRS over 1 plus GMRS. This is nearly RI is nearly RG. This is the self-biased resistance RG. And R0 for this common drain is 1 over GM, some small value. And common gate amplifier GMRD, and the value for RI is 1 over GM, small value of input resistance. and this is R0 is RD in parallel with RL. Here R resistance is connected to source terminal. This R resistance is not the source resistance, but it is a resistance connected to the source terminal. R1, R2 and RG are the bus resistors. This is something very important table which overviews the both FET and the BJT amplifier parameters. This table is for FETs, this table is for BJT. This is common source. The typical value for the voltage gain is about 25. This is minus 25 because when it is phase shift, RA is 500 kilo ohms, R0 is 5 kilo ohms. If you do the same way, this is a common emitter. Here the gain, voltage gain is about 250, at least 10 times higher. RI is 5 kilo ohms, smaller value. R0 is 5 kilo ohms. Here common rated amplifier, this nearly 1. Here also it's 1, but input impedance 500 kilo ohms and output is 200 ohms. 5 kilo ohms and about 20 ohms. And common gate amplifier, again the gain is pretty small, about 25. Here is 250, this 200 ohms, 5 kilo ohms, this 20 ohms and 5 kilo ohms. So what we observed is this, that BJT common emitter and common base circuits have much higher voltage gain than the FETs. And FET common source and common in circuits have much higher input resistance than BJT. And other functions are quite similar amongst these two. So this completes the video here. After completing this video, we'll upload some problems and their solutions, gate problems and their solutions would be uploaded, which are related to junction FETs. And these would be some very typical problems which had been selected here for the presentation. Thank you.